Hello everyone, and welcome to the Space Channel. In recent years, Starlink satellite internet technology has spread widely across the globe, delivering quality internet access to the most remote corners of the planet. However, few people know how it actually works. We've decided to shed some light on that. Let's go. Generally, Starlink space internet is not the first service to offer wireless access anywhere on the planet, but it's the first project to combine global coverage without major grey areas, with affordable prices and profitability. The Starlink service timeline begins in January 2015, when SpaceX announced plans to create a satellite internet constellation. However, the groundwork for this project had been laid even earlier. As always, the US military was the first to require a constellation of satellites transmitting information to Earth. At their request, the Global Positioning System, known as GPS, was created. It allowed users to determine coordinates on Earth with a receiver instantly. The technology proved so successful and helpful that the initially military-only project was opened for civilian use, kickstarting the lucrative satellite navigation market. The example of the GPS satellite constellation was inspiring, so business people in the US and other countries began exploring the idea of launching new satellites that could accomplish a more complex task, providing wireless communication anywhere on the planet. Thus, several satellite communication and internet projects were launched, including Iridium, Globalstar, Celestri, and Teledesic. However, these either didn't survive global financial crises due to a lack of investment or remained niche solutions with limited users. For satellite internet to take off, complex technical challenges needed solving, along with a user model that would attract a large user base. American entrepreneur Elon Musk took on this ambitious task. In 2014, along with Greg Weiler, the founder of Worldview, now known as OneWeb, Musk proposed a constellation concept of 700 Worldview relay satellites placed in low Earth orbit (LEO). Together, they could cover the entire Earth with a broadband internet signal. In the latter half of 2014, SpaceX submitted an application to the International Telecommunication Union to register its satellite constellation. Finally, on January 16, 2015, at a private event in the Seattle Center, Elon Musk publicly announced the plan to deploy the Starlink satellite constellation. During the presentation, Musk disclosed initial details about the orbit for Starlink satellites, which was initially planned to be 750 km, but later adjusted to 550 kilometers or 340 miles as a more optimal height. At 750 km, the satellites would have a longer lifespan, but create excessive space debris, as defunct satellites would remain in orbit. Therefore, the planned orbit was lowered to 550 km, from which satellites would naturally descend into the atmosphere within a reasonable time. According to Musk, the full Starlink constellation would consist of about 4,000 satellites. It is expected to generate between 30 and 50 billion to finance Musk's ultimate dream of establishing a base on Mars. The first batch of 60 operational Starlink satellites was launched in May 2019, after which the size of the constellation began to grow steadily. That same year, SpaceX Services, a SpaceX subsidiary, applied to the US Federal Communications Commission for a license to operate 1 million ground-based receiving terminals. This was another unique feature of Starlink's satellite network architecture. The terminals consist of a modem and a compact lens-like receiving antenna, a phased array that captures signals from thousands of satellites. Using a pizza box-sized satellite antenna to create an internet connection between the terminal and a satellite orbiting the Earth at 550 km is a technological achievement that truly sparks the imagination. This is especially impressive, considering Starlink satellites travel about 27,000 kilometers per hour or almost 17,000 miles per hour. The terminal antenna and satellite dynamically align to keep the radio wave beam precisely aimed between them and exchange data at speeds reaching hundreds of megabits per second. Additionally, the antenna must constantly switch between different satellites every few minutes as they quickly move out of its field of view. At this point, it's essential to understand the differences between a standard satellite TV antenna and Starlink's ground antenna, which Elon Musk often jokingly calls Dishy McFlatface, or simply Dishy. Satellite TV antennas use a parabolic reflector that focuses electromagnetic waves, carrying TV signals from satellites located in geostationary orbit, an orbit that allows a satellite to hover over a single point at around 35,000 kilometers or 22,000 miles above Earth. These TV satellite antennas are limited to receiving signals only. They cannot send data back. In contrast, Starlink's terminal antenna functions as both a receiver and a transmitter of internet data, connecting to a Starlink satellite just 550 km from Earth's surface. Although this distance is 60 times shorter than that of TV satellites, it is still quite considerable for wireless communication. As a result, radio waves between the terminal antenna and satellite must be extraordinarily precisely focused to keep them aligned with each other. With the growth in user numbers, it became clear that providing satellite internet coverage for the entire globe would require an extensive network of over 10,000 Starlink satellites. These satellites, orbiting at low Earth orbit at incredibly high speeds, work together to create revolutionary internet access even in the planet's most remote or previously unserved corners. While this is all well and good, the Starlink satellite constellation has created a significant issue for astronomers since its first launch. First, the satellites, reflecting light, appear like small but quite bright stars in the sky, which interferes with many astronomical observations. In response to numerous complaints from astronomers, SpaceX began painting satellites with a special coating to reduce their brightness in the night sky significantly. However, this does not entirely solve the problem. Second, the signals from the satellites partly interfere with signals from astronomical objects, and this problem is challenging to solve. Currently, the simplest solution is to move radio telescopes to high Earth orbit or to the Moon, which is indeed a straightforward task. However, progress is unstoppable, so astronomers must prepare to relocate to space. Now, let's dive into the internal structure of the Starlink terminal antenna. There are already 3 generations of terminals, each with its own antenna design. I'll examine the second generation, as it currently has the largest number of users in Ukraine and worldwide. These are the rectangular antennas most of us have seen. The rear panel includes 2 electric motors and an Ethernet cable port that connects the antenna to the router. It's important to understand that these motors are not constantly engaged to keep the antenna aligned with the Starlink satellite. They function only during initial setup to orient the dish in the proper latitude alignment. When the terminal antenna is dismantled, we can see an aluminum structural back panel with a printed circuit board on its reverse side. On one side of the circuit board are 640 tiny microchips and 20 more prominent ones, arranged in a systematic pattern. Additional components include the central processor and a GPS module along the circuit board's perimeter. The opposite side of the circuit board reveals about 1,400 copper circles, interspersed with a grid of squares. Next, there's a rubber layer with a honeycomb structure containing small copper circles with grooves, another layer with a similar honeycomb pattern, and finally, the front of the antenna. At this point, most of you probably want to turn off the video, but hang on a second. I'll explain everything now. Essentially, these are 1280 antennas arranged in hexagonal honeycomb cells, with each stack of copper circles acting as a separate antenna controlled by the chips on the circuit board. This massive array, operates using a method known as a phased array antenna to transmit and receive electromagnetic waves directed at the satellite. While the ground terminal antenna is a single phased array, each Starlink satellite contains 5 phased array antennas to connect with multiple ground terminals and interact with ground stations for internet traffic transmission. Another component of the Starlink network is the ground stations, which link the satellite constellation in low Earth orbit to the internet. In the US, SpaceX operates at least 32 ground stations and holds permits to launch even more in the future. A standard Starlink ground station includes 9 antennas, each 2.86 meters in diameter, located on a fenced off 400 square meter area. Ground stations are scattered around the world, excluding countries in the axis of evil and some others, where they are either unnecessary due to nearby stations or are still undergoing permitting and construction processes. Thus, the user's home terminal antenna connects to a Starlink satellite, which in turn links to the nearest gateway, which the ground station connects. As a result, to receive satellite internet service, the distance between the client terminal and the ground station on Earth's surface should not exceed 800 kilometers. Starlink developers are already experimenting with a set of prototype satellites that communicate with each other via lasers, allowing users to be free from ground station range restrictions. Instead of connecting people to a local ground station, lasers will enable satellites to communicate directly with each other in space. As a result, a single ground station could theoretically support the entire satellite constellation anywhere above Earth, with the main limiting factor becoming the bandwidth capacity of traffic through the station on Earth and the satellites, as well as the legal regulations of specific countries. The latest versions of Starlink satellites launched into space are already equipped with functioning optical laser communication equipment. As of September 2024, the Starlink constellation has over 6,000 satellites, and the number of active users has reached 3 million. Starlink offers significantly different pricing plans depending on the user's country. There are 3 types of plans. The first, residential, is the cheapest, intended for stationary terminal installation tied to a location. The second, roam, allows terminal use on the go during hikes or road trips and is slightly more expensive. The third, maritime, permits Starlink use on vessels in seas and oceans, making it the most expensive. The total plan cost includes a one-time terminal purchase with a ground antenna and a monthly service fee. Users have created websites to monitor the variations in Starlink services across countries. For example, the cheapest monthly subscription for the residential plan is in Nigeria, costing just under $24 per month, while the highest Starlink fees are in the US at $120 per month. In most European countries, the monthly fee ranges from 40 to 60 euros, or $45 to $65, with exceptions like Poland, where Starlink costs 335 zlotys, or nearly $90 per month. In Ukraine, one of Starlink's largest user bases outside the US, the current cost is $75 per. Terminals are cheapest in European countries, while the average global price for them is around $450, $500 in the UK, Belgium, and Slovakia. They sell for $250, $300. Roaming equipment costs around 350 to 400 euros across most European countries, depending on the terminal model, and monthly costs are either 40 euros for 50 gigabits of traffic or 72 euros for 1 terabit. In the US, the same equipment costs from $350 to $600, with monthly fees of $50 or $165 for 50 gigabytes or 1 terabyte, respectively. The maritime plan comes last. Here, the equipment costs between $2,500 to slightly over $3,000, depending on the country. The monthly fee is about $250 to $350 for 50 gigabytes, or between $1,000 and $1,500 for 1 terabit. Setting up and connecting the Starlink terminal is simple and takes 15-20 minutes. The antenna kit includes a Wi-Fi router and a power cable. During setup, the terminal app interface scans the area for obstacles and, while operational, generates an obstacle map in front of the antenna, similar to what you see on the screen, helping users select the optimal signal position. Thanks to phased array antennas, the Starlink signal is almost unaffected by weather, degrading noticeably only in heavy cloud cover and thunderstorms. According to specifications, the Starlink terminal and antenna consume 75-100 watts on average. However, these are peak consumption values, including the antenna's heating mode for snow melting. The terminal consumes less, just 40-50 watts in regular mode. This allows it to be effectively powered over long periods by alternative sources such as solar panels, charging stations, batteries, and uninterruptible power supplies. However, there's a caveat. If the power source is turned off, even for a fraction of a second, Starlink loses its satellite connection, requiring a reboot and reconnection to restore proper internet service. Based on my experience, finding satellites and establishing a connection can take 3-5 minutes to, in rare cases, over an hour. My personal record was 2.5 hours from Starlink power on to establishing a satellite connection. Well, that's all for now. Thank you to our patrons and sponsors for your support. You help us improve our content. See you next time.